right, so this is the rolling motion lab. And this one's a little trickier in terms of data analysis. The collection is pretty straightforward. You need a ramp, doesn't matter how long. This is a pretty long one, this is what I have in my classroom. And you need to measure the length of that ramp. The angle doesn't matter as long as it stays consistent the whole time. And then you need 3 different things that are going to roll down. It's really kind of interesting if you take something that is similar in composition all the way through. So here I've got a can of Dr. Pepper, and it's liquid at this point in time. What I can do is then drink the Dr. Pepper and roll it down. And then fill it with water and freeze it, and then roll it down. So there what you have is you have a can that has something inside it that's liquid that's moving, something inside it that is solid, and then empty. Okay? So we'll talk about how to analyze those different things here in a second. But this one's pretty straightforward. Measure the length of your ramp, start your object up at the top, let it go. Whoop. Don't open it yet. Let it go, time it. So if you use Dr. Pepper, you might wait a while before drinking said Dr. Pepper. It's going to get shaken up a little bit. But then it also depends on what your ramp is. This is a very narrow ramp. You know, the first time I did this, it worked fine. Let's try it. That's a little bit better. Anyway, roll it down the hill. We're going to try it one more time. There we go. So it went to the end. I'm nervous. Right, anyway, time how long it takes to go down your ramp. Do that at least 3 times. Get a new Dr. Pepper to drink, and then average your times. The goal of this lab is to compare the gravitational potential energy at the top of the ramp to the translational kinetic energy at the bottom of the ramp to determine how much rotational kinetic energy we have in our object as it goes down the ramp. So the first thing that we want to do is we want to predict the amount of rotational kinetic energy based on our measurements. So let's do that first. Okay, so kinetic energy, the rotational kinetic energy, let's get where we can see. There we go. So the rotational kinetic energy is equal to 1/2 of the moment of inertia times the angular velocity squared. Okay, so none of those things do we know at this point in time. So how about we start with this angular velocity? And we have some measurements for that right now. This is a pretty straightforward one, right? So this is that problem-solving part of physics. We have to go searching for all of those variables. All right, so how do you find angular velocity? Angular velocity is the linear velocity divided by the radius of our object. Okay, great. Well, we don't know velocity and we don't know the radius, but we can find those because those were some things that we found. Now, something to keep in mind is this velocity here is the average velocity. Remember that our object is accelerating. We're going down a ramp, so we don't have a constant motion. So this must have to be the average velocity, if that's what we want at the bottom of our ramp. And then we can go get a ruler and measure that. So to find the final velocity, or the average velocity, not final, we have to take our final velocity and divide it by 2. Okay, so velocity, remember, is delta x over t. And so that is going to be our, I need to make this bigger, our distance of our ramp. I'm going to make this bigger, it's going to look weird. 0.63 meters divided by 0.27 seconds. Now, do not use these numbers. I made this up, all right? I didn't actually have a chance to measure this. I could not find my stopwatch. So I did not measure this. These are made up. Use your own data. So if we take that 0.63 and we divide it by 0.27, we're going to get 2.3 meters per second. Okay, now this is the final velocity. We want the average, so we're going to divide that by 2. So our average velocity is going to be 1.15 math, meters per second. All right, so now we have this part right here. Okay, so we're going to take our average velocity, go get a ruler, measure the radius of your object. Mine was 3.1 centimeters, so it's going to be 0.031 meters. Make sure you convert that, right? Because if we want to divide these, they have to be in the same units. So that is going to be 37.1 radians per second. Okay. All right, so that gives us our angular velocity. All we had to do was find our average velocity and our radius, and that gave us that one. Okay. So now we need the moment of inertia. In your textbook and in your, you can print this off, there's a place to print it off in your notes. There is this document. This is just several different moments of inertia. So remember, the moment of inertia depends on the structure of your rolling object. In this case, I used the solid. Did I use the solid? No, it was the empty can. So this one I used the empty can. If you have an empty can, you basically have a hoop around a cylinder axis. So you would use this one. This is the one I'm going to use. If you have a solid, so if this is the one that you had the solid inside your can, you would use the solid cylinder about the axis. So you would use this equation. If you used like a roll of tape, so say you had some duct tape and you rolled that down your incline, you would use this one. You have to account for the fact that there's a thicker ring over here. You might have rolled a ball, so if the ball is solid, so say you had a baseball, baseballs are solid inside, so you have a solid sphere. But if you use a tennis ball, tennis balls are not solid, so you would have a sphere around the outside. So you have to think about what object you rolled down your incline and figure out which equation that you're going to use. So I'm going to use this one since my can was empty. So the moment of inertia for an empty can is going to be the mass times the radius squared. Now, if you weigh a pop can, it's going to be about 383 grams. So 0.383 kilograms. And my radius is up here somewhere. Where's my radius? Oh, here it is. 0.031 meters. And this is squared. Okay, so my moment of inertia is 0.031 squared times 0.383. That's going to be a really small number of 0.000368, and it's kilograms meters squared. All right, so that gives me my moment of inertia. So now we can go back and we can find our rotational kinetic energy. So we have 1/2 times our moment of inertia times our angular velocity squared, which is squared. So we're going to punch that in. And we get 0.253 joules. Okay, so this is our kinetic, our rotational kinetic energy at the bottom of the ramp. So now we're going to see how that compares to the amount of energy difference between our gravitational potential energy and our translational kinetic energy from our calculations. All right, so at the top of our ramp, let's draw a little ramp here. So here's our ramp. Okay, at the top of our ramp, we have a certain amount of gravitational potential energy. Pen's not writing. And then as we go down, right, we gain in our velocity. So down here, we have a certain amount of translational kinetic energy based on our velocity. In a perfect world, right, our gravitational potential energy would equal the translational kinetic energy at the bottom. But what we're going to find is those two things aren't going to be the same because our object is rolling. And so we have to have some rotational energy lost. Not really lost, but that does not translate into translational kinetic energy. So the first thing we need to do, so really what we get here is what I learned in boating school is, so the rotational kinetic energy is equal to the gravitational potential energy minus the translational kinetic energy. I'm trouble writing. Okay, so we have to find the gravitational potential energy and the translational kinetic energy to find out how much energy we have lost to rotation. And in a perfect world, it would be the same as this. But I made up my numbers, so it's probably not going to be. So let's start with the gravitational potential energy. Gravitational potential energy is the mass times g times h. Our mass we have over here somewhere as 0.383 kilograms. That's a big zero. G is always 9.8. And our height. So you'll have to measure the height at the top of your ramp. Mine was probably about 28 centimeters. I think it was quite a foot. Oops. 0.28 meters. Let's just say 28 centimeters. Again, making these numbers up. Don't copy my answers. So our gravitational potential energy is 0.383 times 9.8 times 0.28. And that is going to give us 1.051 joules. Okay, that's gravitational potential energy. Our translational kinetic energy is 1/2 mv squared. Let's pause that. So we are going to plug in our mass. I think I remember this by now. 0.383 kilograms. And we want to use our average velocity. So 1.15 meters per second. And this is going to be squared. And we have a half in there that I forgot to put at the beginning. All right, so 1.15 squared so 1.15 squared times 0.383 divided by 2. We get, what do we get? This is our translational kinetic energy as 0.253 joules. Okay. So this gives us our gravitational potential energy at the top, our kinetic energy at the bottom. So these are obviously different numbers. So we're going to subtract those, right? Our gravitational potential energy minus our translational kinetic energy is going to be our actual rotational kinetic energy. So 1.051 minus 0.253 is going to give us 0.798 joules. Okay, now, obviously these two things are not the same. Again, did not measure. Use your own data. But you're probably not going to get exactly the same, just because real world, there's a little bit of friction up here. You're losing some of that probably. There's different reasons why you might have different answers. But what we're going to do is we're going to find our percent error, right? So this is our real, and this is our ideal. So to find percent error, remember, we're going to take what you got, your what you got, your real number. Let's just write that out. We're going to subtract our ideal, and then we're going to divide by our ideal. So our real was 0.798 joules minus 0.253 joules. Then we're going to divide by our ideal, 0.253 joules. So we are going to get, and then of course this is multiplied by 100%. So I get very high number, 215%. So I was way off. Maybe if I actually measured it might be better. So this is how you do those calculations. So we're looking to see how close you are to your actual measurements. Okay, how much kinetic energy, rotational, do you get actually at the bottom compared to what you should get based on its momentum of inertia?